Welcome to this new tutorial on models and code. And this is an exercise, step-by-step exercise on how to model a floor plan by numbers. As you know, my hypothesis is that space is not about the visual or graphics. Graphics is always a rhetorical figure to convince people. Architecture, space is about, you can talk about it, so it's about putting realities into differences, into proportions. And the medium for that is the proportion of numbers. It always had been like this, and in all architecture, in my understanding, it is like that. And we have to re-establish that, especially with the rhetorics of this super advanced simulation of reality with our actual computer tools. So let's go for modeling floor plans by numbers, and you will see this is working quite impressively simple in its setup, and you can address all architecture to this. So it's unusual, but I think you will get the idea. To get an overview, I made a summary. So you see all the numbers here, a few numbers, and then you see the artifacts. So to run that, take a copy for your desktop. It's better on your desktop. Have it here. Sorry for these mistakes, these errors. I have to fix that. We will go in detail. This is here, so don't be afraid. These are 18 steps. We'll go in detail, step by step. Very few elements in these steps, just to discuss the whole story of how to do that. So this is a summary. You get a picture of a floor plan. You get the coordinates. These are rough coordinates, and these are correlated coordinates. So take the rough ones, for example. Then we can see this. This is step one. This is a program to run. You can find the code here. So we see the image and the key points. First step is to get the axis, for example, index 22, 23, so it's a coordinate here, 22, 23, wherever they are. So you can move them around, and the axis will change as well, will follow. So these are the anchor points, and from then on we only work with indexes. So axis in XY direction, axis in Y. For example, 22, 27, this is here. Put it here and put the axis in X and in Y. These are the axes. This is what we can do with it. We take all these axes. See, the uncorrelated data is not orthogonal at all, just points with offsets. So you can do any kind of geometry with this methodology. So this is the plan. Now we have all the intersections of the axis as vertices. Next step is to define the faces of the rooms. So this, for example, is 1, 37, 38, 2. We find it here, 1, 37, 38, 2. Render that, get the faces, render that, and here we see the faces, and you can select them. So next step is the doors and the windows. For example, here is the segment 44, 43, which is here, 4, 3. It goes from here to here. And we place there a 90 centimeter door. The center of the segment is the center of the door, and the door should go right side. So it's from here to here, center, right side, because I don't like a door like this. So if you, for example, go from 43 to 44, then this should be left side. Good, do this all with all the doors, all the windows. Render step 4, get an overview of the things, the windows and the doors. Make an analysis of the rooms. This is a graph how the rooms are connected, and it's we calculate the number of centrality which qualifies a room, because this is very central because it's connected to the other central room, so it's getting importance by its centrality is depending on the centrality of its neighbors. And this is how Google weights the websites, and this is a certain algorithm for weighting and qualifying a network. I think this is more interesting than classifying a room towards specific functions, like a kitchen, a living room, bedroom, and so on. So I think it's more important just to have the proportion of the room, its centrality, or its temperament. And by that, then a room will invite different functions, whatever is coming. So it's not specific, it's not defined, and so on. But I think that is adequate for rooms and architectures today. So therefore, I'm skipping the naming. It's just with indexes, with numbers, proportions, centralities, and so on. All these kind of numbers to describe buildings. So if we have that, this is automatic. We give the walls and the facade a width. So we have it here. And then we go to 3D. The height of the walls, height of the doors, and then the height of the windows. This is a very straightforward, not optimized procedure. The code is from scratch is in this notebook, and therefore it takes a little long to make all these intersections. So that's a 3D model. So we have these numbers, indexes and coordinates, these numbers. Then we generate a 3D model. We can export that. Go, for example, here and say floor plan 03, and you can do OBJ, wavefront, or X3D format. This is working. Save that, and we have it here. Now go, for example, to Blender. Import. This is working, this is working. Desktop 3, and here is our generated floor plan. Go here, cycles, go with the light, sun, and so this is another problem how to make that proper, but I think you get the idea and see that it is working easily, smoothly integrated. So we have this, and the next step is just to get all the walls, and put them on a workbench for prefabrication or for calculations, for qualifying them, giving them certain surfaces, go for the windows and ask how to qualify them, and so on. And these are all the lists. So this is what we need in building information models. So we have the elements, we have the square meters, for example, facade, and the floor plans. And you see it's a non-regular, non-correlated coordinates. If you want to change that, very important to see that. Now I correlate the data. Now it's different. The axes get different. So, but not the numbers, just the coordinates get different. The facades get different. So the faces, the rooms, now they are regular. This is not changing the position of windows and doors. They are just adapting. You see. So these are parameterized models. So this you can't do with graphics. This is stable. The same here, and now we have a correlated coordinate list. So having this, you see, and then of course the square meters they are changing then, and everything is up to date. All this is automatic. So having this, why is this important? So it's not, of course you can say, yeah, but if I'm drawing that, it's fine, and I can, so if you have these numbers, you can, so architecture is, yeah, you have to address what is going on. So with the graphics, you're kind of isolated. If you want to have it connected to what we experience there in the internet, you need another setup. These, for example, these are towards 6,000 floor plans and the map. And the map is organized towards X and Y dimension and the numbers of rooms in X and Y. So, and you see these are small, and then these are the long ones, these are the square ones, and few rooms, multiple rooms, and so on. So this is a map of the landscape of floor plans available in this set of 6,000. Imagine you're having 600,000, 6 million of them, like you have it with the internet. They all are organized. You can look at one of these guys. They are organized like we had it. So you have the reference, then you have the axis, you have the rooms, and you have the segments. So the walls, openings, doors, and windows. And you have a transformation, where to put it, how to rotate, how to translate, how to mirror and scale it. So that's a transformation. So if you have this guy here, these are his friends. So they have a similar setup. So, or if you take this guy here, this is the detailed as we had modeled. So it's just the rendering of these few numbers. So we can do 3D, we can do it to Blender, or whatever. So, and we can ask for the source of the floor plan. So this is how it was drawn. So in this case, it's a kind of misunderstanding because it's just the two floors. So take another one. Here, it's another one. So, interesting is this. So we can say, for example, we want to have 14 meters by 9 meters. Make it 10. So, or make it 12 here. So now these are, they all have 12 by around 12 by 10 meters. These are the friends, and this, for example, is my parameter. I can move these parameters, for example, rotate it differently with these transformations, rotate it, move it just by, so now it's here, and I can go and ask for all the different things. They all got adapted in their parameters, in their parametric setup. They get adapted to our parameter. And I can select, done, boom. And can go and take that and adapt it and optimize it, get ideas or whatever. So this can't be done with actual graphics. You need these systems of numbers to be able to calculate with it. So that's to give you an idea what we did. Now we need this one. Here, in our Beyond the Grid, this is a book where we had our principal research in AI, computing, in applications in architecture before we run into theory of that. So, and this year is 2007, so it's towards 15 years old, and we made this. So we had a parameter, and these floor plans are famous, or the most prominent floor plans, 100 floor plans of Zurich, and we just aggregated them within the parameters. These are the parts, the rooms, 3 floors, different setups, how to do it, and people can choose, or a machine can choose, or a market can choose, and so on. You just do it. So all this is not about architecture, I want to say, but you simply can do it and please people with things you know they work. So this is, people didn't like that, so we went to theory, but this is how I think we have to start to talk about and to specify, to articulate architectural proportions, because then you are connected with graphics. You stick to the ground of reality. So it's getting more rational things you're able to talk about it and combine things, make differences and so on. You can't do it with the reality of graphics. So let's go for detail. This is an image of a floor plan. You simply can copy and paste any image in here, take a photo or make a scan, or get it from internet, get it from these real estate environments, just put it there. Important is you have to scale it in a proper, you have to put it in a proper scale. In our implementations here, we need 1 pixel per centimeter, so it's 100 by 100 pixel per square meter. So if you don't have that, for example, you can take any picture, you can ask what is, you can do it with Photoshop of course, but here, now it's 1577, 9. So if you simply say from here to here, it's not 15 meter 77, it's 14 meter 60. Then you simply go and say a resize image resize of the image. This is assigned to this, to be sure, assign it here. And then you say, in its proportion, put it to 1/400, because this is 14 meters. And then we get it here, and then our image is 14 meters, and this is proportionally reduced. And then we have it in another scale. This is how to do the scaling, and simply say then, if you want to have that image, assign it to image again, and then you have that, you can delete the old one, and that's it. But this is 1577. So very simple to get a floor plan. Now with the anchor points, the key points. I think you've seen in the other modules that in most cases, for example, with skyscrapers or with factories, office buildings, even with, so it's more a systematic way how to get the access and so on. Therefore, you can do some code to create the points. In this case, it's completely arbitrary, so therefore make the stupid unstructured way, which means you can go here and take this tool here, and then you can get the coordinates, the important ones. So take whatever you do. Then you see here, these are some data. Copy that. No, copy the coordinates, not the indexes, and paste them. And then you have the coordinates in a super crazy resolution, and we will curate that soon. This is a proper one I already did. You have to make it complete. Here you see, you can iconize it. These are the coordinates I selected. If you go here and then you can say iconize selection, then this crazy stuff is hidden in this box. Now these coordinates gets indexes, so we calculate that. You will have another number, so I put in 27 coordinates, therefore it's 27. So this is to show the coordinates. We have to evaluate here, and here I show them. So you see it's a little crisscross because we can't make it precise, so we have to curate it. That will be the next chapter. So this is how to do it. We say highlight image is the image, and then you put a graphics in the foreground. In this case, we put two things. First is the points. In graphic complex, this always needs the coordinates, and then the indexes to the coordinates. So it's directly these coordinates, indexes, make point at if all of them in red. And then we go do the same thing, but within numbers. So we make it with a map index, insert the number at a certain location, plus 10, 10, therefore it's a little offset here, and left bottom is 10, 10 of the center of the circle, and that's it. It's highlight. So you can take that, it's always working, you don't have to implement that. So that's the step 2. Curate. So you can, for example, cluster and round them. So for example, I simply say in X there should be in X direction there should be 10 different lines, and Y 8 different lines, and then you simply say round, snap it to these clustered X and Y's. So you see, for example, here, if you take this out, you have the X coordinates, Y coordinates, and you see these are the X axis. If you want to have 10, these are the prominent X numbers. And then you round the coordinate, the nearest in X and Y, which means X is then always one element here, and Y is always one element on, say, Y. So that's one method. So then, for example, you also can say align the coordinates, the anchored coordinates, and you simply just want to align 23, 11, 10, 9, 24 to X, align them to X, and these 3 to Y. And then this machine here says, okay, if it's an x, then I take all the different x's and align them to their mean value. So these get an axis, these get an axis to force it. Like that as well. Then you can see the current data set. So now what we did, for example, we put these to align, and now these to align as well, so you don't have this crazy, unfortunate edge here. So, or you can do it, the whole thing manually, or simply say the coordinates should be like this, and then you make it. So there can be thousands of ways to do that, but you have to correlate them. Export the query. So if you want to have that, you can have, this is how to make a table. This is used with the function data set. And then you get, to make a table, you make an association, and the association is this. You have a key, it corresponds to the column, and then you have a value, a key, a value, a key, a value, and put that to an association, and make that a data set. So, and then we get first point, x, y, done. If you want to export that, we will have it later. To Excel, no problem. Now, the axis. So, if we have proper coordinates, now I say I want to have an axis from 23 to 22 to 23, and so on. I make these things explicit. You can go for an automatism there, but I think it's more robust if you do these axes. So this here sorts them from x, from left to right and from bottom to top. So you can put it in any sequence here, and these sorts them. And this again is just, you see here, x is 1, 2, 3 and y, and x, and these are our points. Our segments here, so we said it's from 22 to 23, these are the segments. And these are the points of intersections. Good. Go for documentation here if you want to understand that. There's his online documentation. Go here, I think. It's not too complicated. So, to make it more generic, now you can take all these x's and and get their crossing points. You can analyze these. It's using region intersection tuples. With tuples you make combinations, so or combinations of x and y axis. Make the interconnection, region interconnection, and then look for the points. So now we have these coordinates. These are the vertices. And now we have a more systematic grid constituting our building. This is how it looks like. So, no difference, just more points to be more generic. Okay. Now the faces. If you have this grid, you simply say 1, 37, 38, 2, 1, 37, 38, 2. So take that, for example, out. Then you see, and this is my first room, and these are the other rooms, and look at them. That's it. This again is always the same. Don't have to touch it. This is what you have to edit. You have to decide as an architect to play the proportions. Good. Windows and doors. This is a code for the window and for needed. And again, so let's, for example, it might do it like this. So take the doors, copy, and highlight it. So then you have these two doors here. And now, for example, this says I want to go from 44 to 43, 90 centimeters. Make it one line. So, and make that. So now 44, 43, 90 centimeters. For example, go for 60 centimeters and it's getting smaller. So this says it goes from 0.5 in this segment. If I go to 2.2, then it's going, because it's starting at 44, going here, then it goes to here. And this is the, the center point is going to 0.5 of the whole segment. So this is 0.2 of it. If I go here on 1.0, then it's this point here. If I go to 0.0, then it's going here. This is 0.2 of the wall. So take it 5, take it 5. So this is the proportion of the segment, where to put the proportion of this door. Yeah, and then take 90 and this here. This orientation, this is left and this is right. Left, right. And you do it with all the doors and all the windows to get this set up. Very simple. Good. Next step. Now we analyze the data. So this, for example, says here. These are the faces. So we have faces. So here indexes 1, 37, 38, 2. So we take, for example, just the first 1, 2, 1. So these faces are put to coordinates. The coordinates had been this. These had been our coordinates. So if I take coordinates of 1, that's the coordinates of this index. 37 is the coordinates of this index. 38, and so on. So therefore, if I take this here, coordinates of the variable, pure function, mapping a list of values. This is a list from 1 to 1, therefore I need this list if I want to have it single, then I take this and get the number out. So this means give me the coordinates of faces from 1, this is this thing, and he gives me the coordinates of these indexes. So what I'm doing here is getting all these coordinates and applying them and making them partition. So partition is this. Partition says if I have a list of 2, 2, 3, 4, 5, so I put them into 2 parts with an overlap of 1, and I have 1 to make it a loop. So this goes 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to the beginning at the 1. If I keep that off, then the last one is gone. So this is what partition is doing. If I put here 2, then it goes 1, 3, 3, 4, 4, 6, and so on. So this is the overlap. So which means this is our room, and if I want to have the segments of the walls, I take these from 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 2. This is indexes here. Yeah. So that's working with partitions, which means if I go here from 1 to 1, this says this is a wall from here, a surface from here of this room, from here to here, from here to here, in coordinates of this room. So do the same with the doors. Understand that. Doors, what is doors? Doors looks like this. Doors say from here to here 90 with these segments. Then I wrote a function doing the job, because this is a little complicated to calculate, which means if I want to go from door list, door mapping always needs lists, therefore I say 1 to 1, not to get too confused. Then you have a door from here to here. So we have that. The same with the windows. So and now we go here. Doors to rooms is an intersection of, we simply say, we make an intersection of the doors with these surfaces of the rooms. And if they intersect, then we make a connection. And so on and so on. So this is the principal idea of how these things go. So you don't have to bother, just to give you an idea of how these things works. This says the first list, so this is not rendered here, this is not rendered because of a semicolon, it is not, but these are the lists rendered here, doors to rooms. So door 1 is with rooms 4 and 5, door 2 is with 4 to 6, door 3, 4 to 6. So the same with windows. Window 1 goes to room 9, to room 9, and so on. And rooms to rooms now takes doors and looks whether a door, what are the 2, so the doors are always 2, because door 1 goes from 4 to 5, therefore room 4 is connected with room 5, that's here. 4 is connected with 6, and so on. Needs some correction, and that's it. So by that you get the connectivity of your elements. This is done like this. With this you directly can do the graph. Take the semicolon out. So this is a graph of these rooms without coordinates, but you can get the centrality. So you simply see this is more central than this one. This is more central than this one. This is more central than this one. So therefore these are prominent, and you see these are the numbers with the PageRank centrality, and you can look it up in the documentation as well. So by that we got the centrality. Show that in our setup. Now this is a graph. The graph now gets, here it's just a graph. It has no form. A graph never has form. If you want to go and specialize that, you need the vertex coordinates and put that to our rooms, in the center of our rooms. And then we have the vertex label style. Now vertex size is the centrality. This is what we had here by that. And vertex labels is red, font size, bold of the number of the index. By that we get the room number, centrality, and its location. So it's a little tricky to find out all these different options, that it's working well, but you simply can copy these things. But for this exercise, you just use it to see the analysis of the topology of your floor plan. Good, nothing to do, just works automatically. So this is another, so we had now the graphics, we had the graph, and now we go for regions. Regions have that's geometric computation, and you can work with areas, intersections, and lengths, and do all these kind of calculations. We can put with our coordinates, with the faces. You see the coordinates again, if you want to see that. These are the coordinates. The faces, they are always the indexes. So you work like this. We do it with the graphics complex. We do it with the graph, and we do it with mesh regions as well. So what we simply say, we make a mesh region, and the rest is mesh region of these, make a polygon of these faces, and then we have just options to make it proper looking. So, but now we have a data structure where we, for example, can ask a mesh region, what is the primitives of 2? So these are the polygons. These are all the lines, so one-dimensional. These are all the points. If you want to go, and you can say cells, then you get the points with the indexes. Instead of primitives, you get the indexes. Here you get the lines, all the segments, and here you get all the polygons. So, and you can do the primitive, you can, for example, do the areas. So, which means these are the areas of our rooms. Then there's interesting, what you can do is, just for your information, you can work with units. It's called a quantity. You say these areas here, it's a quantity, and this is centimeters by centimeters, because we have 1 pixel per centimeter, other one as a centimeter, so it's square centimeters, so it's centimeter multiplied with centimeters, and we want to convert that to meters by meters, and this is now these numbers in square meters. Or we can have the total of this area, these are the square meters. We also can do with these mesh region to get the bounds, so which is a complicated task. If you have this kind of setup, finding which side here is outside and which is inside, if you want to make an algorithm for that, it takes time. So it's super simple here, just say boundary and you are there. Or the length of the facade now. Primitive bounds, this was here, mesh primitive bounds, this is all these lines. And yes, now we take the arc length of the facade, because the bounds are here, so we take the length of this, and this is the facade length. Total. So these are the calculations. So if you are with these numbers, it's super direct and straightforward what in principle you need with your building information models, with the calculations, the lists, if you want to go to quantities, to costs and so on, directly there. Or the length of the internal walls. Now in units. Wall length. These are all the walls with mesh regions, not only the bounds in square meter. These are the meters, inner walls. So now it takes the total walls minus facade length in meters. So the inner walls are 60, the outer walls are 44. So all these numbers, just to get an idea of what it costs. Counting, you'd simply do this. You have windows. Windows was, for example, this. And you simply say count by, for example, and then you say count by the second element of it. It's a pure function, the second element. This is the whole thing. This is one element we want to count. And this second element we want to sort out. So we want to count that. And then he says, yes, at this position, width of 90, there are 9 windows of width of 90. If you go for the doors, we have 8 doors 90, 1 door 2.20 meters, 1 door 120. Count by. Good. These are some numbers. Now the rooms. Some helping functions. You can look it up, but you don't need to make it running. So this is, for example, all the mesh. So we summarize what we had before. We have the mesh region as we had it before. This all the mesh, just the coordinates and the faces. So then we have the boundary mesh as we had before, and now we just highlight that just to see this is the all mesh, this is a boundary mesh. So then with these functions here, you have them, for example, clean the polygons if they are if they are points. If you have a straight line, there might be points on these grid points on this line. We want to have it on a single line. That's the cleaning. Then we close the polygon. That if the last point is missing, last line is missing, then put a line in here to close it, and then we make an offset. So, and this works like this here. So, for example, we have the mesh region, bounds 2, that's a polygon. Polygon is this. So, and then we can say parallel polygon. We don't need close, we just say, I think it works like this, polygon, and then 10, polygon, so this is how it works. If you want to see that and illustrate that, make a graphics. So we say polygon of these numbers, and we say this should be light gray, comma, then you get the polygon. If you want to see that, you say the coordinates frame true, then you see the coordinates. That's the room. The numbers looking like this. If you put these numbers into the parallel polygon, now we can say red line of this parallel polygon. So we have this polygon, the same thing, parallel polygon. So this what this setup here. So the same setup, and here red line. Why is it not working? Ah, it's there. It just looks. So then take 10 or 20. It just looks like an error. So now it goes. You see how it can be done. So this is used. Code how to do that is here. This is used to get the floors and the walls with a depth. So we up to now we had just the axis, and now we get the width, the facade, and for the walls. So if we have that, we can go for 3D. This simply is very simple to do. You get a height, and now, for example, we have the wall surface here with the floor. No, let's go for example, wall 3D. We have the wall surface. These are the red lines, or get with the facade surface. Facade surface is a blue line at this here. So if we go for facade surface, 1, 2, 3, 4. So you see these are coordinates of the facade. This is a blue line. So what we simply want to do is now we go for 3D. Yeah, and we do it like this. Let's check. So what we do is, again, we partition that into 2, 1. So because it's closing, we don't need the one here as well. If you put the second one, then you get this point. It's not needed. So now we have these pairs of numbers, which is then one of these lines. So to make it 3D, we need a polygon going here, going up, going back, going down. So which means, and we always can say here cases, take a key of this, and then we say we want to have these points. This is P1, or just x1, y1, x2, y2. So this is a key. We don't need this. So, and just, for example, take just only the x, x1, x2, just to illustrate that, and we have that on the first level, second level. So, and this takes only the x coordinates, x2. Then we have only the x coordinates. So you see, yeah, this goes in x from stays on here. This stays in goes to in x. This stays on x, goes in y. This goes in x, and so on. So you always take something, make a key, and do something with it on a certain level in these hierarchies of data. You can put all, but then it's always confusing because it's looking in depth. You have to be very precise with here. The second level, 1, 1, 2, and on this level we want to look the elements and check them for this key to find them or to replace them. Then you replace them. So that's so now what we are doing is we go here and simply say, instead of x1, x2, we simply say we make a polygon from x1, y1, 0, x1, y1, h, x1, y2, h, x0, and do that. And then we get 6 polygons going around here. Doing the same with the walls and bring that to graphics. It's giving you a 3D model of your system, fully automatic. You simply need this parameter. So do the same with the doors and the windows. Simply works the same. We have an extrude function here. Do it with the doors and the windows. Look at them, combine them with the graphics, and then you see we have this red, this room 1. Oh, this is room 2 here. Where's the red one? Red, this is the room. Opacity. And then we have all the doors, all the windows, and the facade. So, if you have that, now you cut these helper functions, and you can imagine how it works. Now we take all the facade polygons in 3D and try to make this this intersection with all the doors, and then we have that, put that to graphics, and then we are here with the floor plan with its openings. Simple. So what you can do now is very interesting. So you see, for example, graphics 3D. So we have to go to 3D with graphics. We simply say the floors, the facade, the walls. So, and these are parameters for the graphics, but this is the code for the graphics. Go here and ask for it, and then you see what it is. A lot of polygons here, a lot of polygons. So you can take them and say, this is my floor plan 01, and symbolize it. So you can have 100 other floor plans just with other symbols. And now you can work with them as graphics. So you can say graphics 3D and put them, so this is the graphics, and then you say floor plan 01 should be there, then you get it. So you can do another floor plan, say floor plan 01, and then you say graphic transformation, and then translation transformation of 250. So this says whatever it is, move it 250, graphic transformation. Full is geometric transformation. I made this short, and this is translation transformation. So do that, and you have two of them. Then you can go, for example, and take these and say geometric transformation of these two things here. You can build your hierarchies, as we know in CAD systems. Geometric transformation, and then we say rotation transformation about that's 45 degrees around the point. I'm not sure. You have to look it up. They need an axis, so we want to have a z-axis. Here we are. Now it's rotated. Yeah, or make multiple copies and so on. So you can have and these things. So you simply can take that as a graphical symbol, whatever you do. And by that you can work with thousands of floor plans if you want. So therefore all these fine granular working is just to prepare a principal data set. And things by symbolization, they stay simple. That's important. Good, and we still can do the calculations here, the amount of rooms and so on. Just work on FP01 or work on this graphic and say this is FP02, and then you have this aggregation of others, and then it's a symbol again, and so on and so on. You can do all the calculations we implemented and discussed above. So now the export. We showed it in the beginning, so it's no problem with this. The key problem is two things. In CAD systems and with this exchange format, the X, Y, and Z is changed. So what we need here is, for example, if we have the facade surface, we have these points. No, we need the 3D things. So, for example, we take this as temporal. This. So now we can say cases and go for temp, and then we ask for these three-dimensional coordinates. So we say X, Y, Z. And we want to see X, Y, Z on I don't know which level. So these are the X, Y, and Z's from all these polygons. I think maybe it's level 3. Yeah, and if you go for level 2, you can find them. Level 4, level 3, you find them. So these are the points. So, and in Blender, X, Y and Z is changed. So we simply can say Z, Y, and then they changed the things. So simple like that. If you're sure with that, you simply say replace, and then you keep and then you get the things changed. You can do that with our graphics as well, but so this is the first thing we need. And so we have graphics is here. You'll make, for example, say graphics, GR 3D, and then it's changed. Oh no, it's take all. Then it's changed, yeah? Because there's a data structure, we've seen, you take this key, it's a little risky because there might be other X, Y and Z's, but it worked, and change it and everything keeps the same, the whole structure keeps the same, and then you are there and change these things. The next thing is we go from centimeters to meters, therefore we need to go here and say this should be divided by 100. Now the key was not specific enough. Now I put here and say it should be a real number, and now it's working. So if we go here with frame true, framed or boxed. No, it's a okay. Then you can imagine now it's with meters instead of centimeters. And we have the problem that Mathematica has endless amount of endless numbers. So for example, we can have n of pi. We can have 100 or 1000, and you see this is not compatible with the exchange formats. So you have to make explicit that this is round to, for example, so you always have not so high resolution in CAD systems. So these things have to be adapted, and this is done with this simple function, and depending on where you go, it's different. So in our case, it's with Blender, it's always like this. And now you can go with OBJ wavefront or with X3D to export it to Blender as we did before. That's it. Now the surfaces. So we take these graphics, DE, graphics, and we go for the facade. So what is it? Facade 3DC, so it's this here. Let's have a look. So we had this was not our thing here. Floor, facade, walls. So this is what we had. We have it here. So we don't have the colors. So therefore, floor, facade. So this is what we have, because GRD was this, and first, second is this. So we take these parameters. So if we have then go here, copy these, then we have the facade elements. Go with the area, quantity, meter by meter, done. So we don't have centimeters here because now it's meters. And then put that for all the walls. Walls 3D. Yeah, okay, centimeters. I think go through, it's not super surprising how it goes, and then make these lists of the elements. So just these elements, put them in a grid, a column in a grid, and display it like on a workbench. This is a function how to get it from wherever it is to 0.0 2D, back to 2D 0.0 here to make simple calculations, or it's kind of workbench to do the production. And then you have a transformation function, this geometric transformation, to put it back on site. So therefore you need always only these elements and their transformation to put it somewhere at some place on this planet. So that's it. So what I expect to do is that you do your own floor plan, you go through these steps, and you make a 3D model in Blender, render that, you make these kind of calculations and smooth analysis and presentation of your floor plan, the data and the 3D rendering, the components, and make a nice discussion of your floor plan in the full spectrum of things I explained. But in principle, in summary, it's just these steps. So, thank you for watching, have fun, and see you soon.